talking about magnetar with multipolar magnetic fields. Let's welcome Yamasaki.
Thank you for introduction. Again, magnetar. Sorry for this kind of compact object talk. So this is the picture. Maybe most magnetar guys like. This is a beautiful picture of magnetar. And I talk about a small-scale magnetic field potentially existing on the surface of neutron star and how these affect the observational feature of radio emission, like fast radio burst. So this is the content, and thanks to our nice formal talks, I can skip this introduction. So basically, I talk about magnetar because it is the leading progenitor of fast radio burst. And we have one strong evidence. Actually, it's kind of very strong evidence that FRB is at least coming from one magnetar. So there is a good reason to study magnetar in many sense. Then talking over theory for producing FRB. In the previous talk, there are two models, nearby model or faraway model from neutron star. And here I focus on pulsar-like model, which is considering particle acceleration in the polar region of the dipolar magnetic field. For example, here, this is a FRB model. And this is quite similar to pulsar radio emission model. We usually consider pure dipole field and particle are accelerated in the polar region. This is an open field line where particle can achieve very high Lorentz factor, such high energy. And so this is both assuming a dipolar magnetic field. Then why we assume dipolar magnetic field? Because nobody, everybody hates our kind of complicated mathematic form. Dipole is the simplest form for magnetic field structure. And also because dipolar field is most dominated, it's dominant around the neutron star. If you go far away from the star, small-scale magnetic field contribution is negligible. And when we observe radio pulsars, for example, and the information coming from radio emission is mostly coming from faraway region, where only dipole field contribute a lot. So small-scale feature is usually kind of invisible. These are the reasons. And then now, I don't talk much about this slide this time. I talk about later, and even when discussing implication. But there are a lot of kind of evidence suggesting maybe pure dipolar magnetic field have some difficulty in explaining observational diversity in radio transients, including magnetar radio emission and also fast radio burst. Then motivation. Actually, we have one strong evidence in magnetar. This is the kind of direct evidence of indicating existence of a small-scale, very strong magnetic field. So this is the X-ray observation of famous magnetar in 2013, and this is the this magnetar has a pulsation in X-ray, and this is a light curve spectrum of the magnetar radio X-ray pulse. And at some phase, we see kind of special absorption feature likely coming from proton resonant cyclotron emission line expected in very strong magnetic field. This indicates actually 10 to the 15 Gauss. And however, from rotational information, we measure this is likely 10 to the 12 Gauss. So there is a huge gap here. And actually 10 to the 15 Gauss, this measurement is more direct observation of magnetic field strength. This means there is also a non-dipolar field structure, 100 times stronger, maybe multiple structure in magnetar. This is the one observational evidence in nature. And another evidence coming from recent nicer observation, again, X-ray observation of radio pulsar. And actually, there is an expectation that in a pure dipolar scenario, radio emission location on the star and the X-ray emission location on the star should be the same. However, clearly you can see, the location is inconsistent. X-ray coming from here, radio coming from here. This is likely dipole, but X-ray coming from different location. This means, again, existence of multipolar component on the neutron star. Then, now it's, we have an observational fact that implies small-scale magnetic field which could be strong actually near the neutron star. Then let's rethink the model for dipolar-based radio emission model for magnetar radio emission and also FRB. This is natural direction. Then the question is how this existence of a multipolar field can change the particle acceleration region, I mean open field line region in the polar region. So then we want to test how this changes the structure of the radio emission. So method is simple. So we use analytic previous model using two parameters. One is so basically we consider as a first order, we consider quadrupole component on top of dipole field. So there is higher order magnetic field here for component. This is pure dipole. Then these two are superimposed. And we can adjust the strength of the quadrupole. So this is the ratio of the magnetic field structure, and we can actually misalign this component. So this is pretty simple model, but very useful. Then actually we can estimate how strong can this quadrupole field strength compared to dipole field. Actually, there are many arguments, but roughly speaking, this ratio can be actually 1,000, up to 1,000. So this is theoretically reasonable range. So we can change this ratio of quadrupole to dipole field ratio from 1 to 1,000. So this is the basic assumption. Then let's see the result. So first, setup is very simple. Typical magnetar, slowly rotating magnetar we consider. This is the neutron star. And we consider highly misaligned quadrupole dipole geometry. So basically, dipole is like this. This dashed black line is the dipole polar open field structure. And the quadrupole is around here. Then we change the strength of the magnetic field of the quadrupole. So when the magnetic field is, this ratio is very small, it is very similar to dipole. But after increasing up to 100 or so, we can see significant change of the open field line region. So this is basically where radio emission is created. Then this is the one thing. Then next, we can check the viewing angle of this open field region. This is the angle measured from the polar region. And then in case of dipole case, pure dipole case, it is pretty simple, just monotonically increasing. However, you can see huge radial dependence. This is the neutron star radius from neutron star in units of neutron star radius. And there is a dramatic change depending on the radius from neutron star in viewing angle. So depending on this viewing angle, this determines how we see radio emission. Then also beam width, so basically the angular width of this open field region also changes compared to pure dipole case, which is very monotonic increase. Actually, we can have a much larger beam width of the pulse compared to pure dipolar case. Then I discussed the implication. So one implication is actually temporal structure of the radio emission. This right panel shows the right curve of some repeating fast radio burst. And you can see multiple, this is the time and frequency, and this is just the right curve. And you can see three kind of pulse component. It's not a single pulse. And also this is also complex structure. And so basically we have multiple peak structure in fast radio burst very often. And this can be potentially explained by this multipolar component. This is the reason why. You can see, for example, if you consider given observer viewing angle, there is always one or two, maybe two or three solutions depending on the viewing angle. For example, for this viewing angle, radio emission is created here and also here, and these two emissions can be seen from observers. So this can be observed as a multi-component right curve. So this is one possibility and the implication for fast radio burst. Then the next is similar argument, but because this polar cap region, open field region has very strong dependence on the neutron star radius, it changes curvature a lot. So even small change in the acceleration region from neutron star. So if you assume some specific emission height where particles are accelerated and create radio emission, small change in this radius can lead to the very large variation in the observed viewing angle. So this means we can easily miss radio emission from pulse to pulse, from epoch to epoch. So this may explain, oh my, sorry. Um, Somehow, I just need to show entire. Could you help? Sorry. Thank you so much. Okay, I can go with this, maybe. It's too small. So, oh, thank you so much. So FRB burst rate actually depends on epoch. It is not always very active, like hyperactive repeater. And this is a time, and this is a burst rate, number of bursts per time. Actually, this highly depends on the epoch. This might be also depending on this kind of small scale multipolar magnetic field structure. And finally, quickly, so basically, actually, magnetar has also radio pulsation, which is weaker version of fast radio burst. And this has a much higher beam width compared to typical pulsar population, and this is against theoretical expectation. However, if you consider quadrupole field, this can increase the beam width of the radio pulsation. So this can potentially explain this kind of feature too. So I summarize the takeaway messages. Basically, there is evidence that theoretical and also observational motivation that magnetar has multipolar component. And then why not consider this when modeling theoretical radio emission? That's all. Thank you so much.
Just a quick question. Can this model be used to explain the giant radio pulses?
Giant radio pulse.
Giant radio pulses for incredible and other pulsars.
I think I'm not familiar with giant radio pulse, but in my view, giant radio pulse production mechanism is maybe different from typical, I don't know. So the location of the, emission region can be, some people discuss, it can be much, much distant from the neutron star. And I don't know, sorry. Maybe direct connection between giant radio pulse from pulsar and the fast radio burst is maybe a little difficult, but I'm sorry. What kind of feature of giant radio pulse you want to explain?
No, the origin.
Origin is outside the scope of this work. Sorry.
No, okay.
I'm not sure. Sorry.
Can you go back to your previous figure?
Sorry, this is different.
This one.
Mm-hmm.
What are the green contours?
Sorry, this is millisecond pulsar, and this is pulsar. This is pulsar in a binary system.
Yeah.
Sorry. This is all pulsar, which is expected to follow this pure dipole expectation. However, magnetar is outside this kind of expectation. That's the point.
Okay.
There's a question in the back. Right there.
Hello. So, do you have considered the the duration of the pulsar spinning effect on this FRB mechanism or?
Yes. Actually, if the pulsar itself is rotating very, very fast, then of course the picture shown here, for example, pulsar rotation can be potentially higher than the time scale of the particle are accelerated along this line. So this can happen. However, the main focus of this work is not pure radio pulsar, but radio emission family coming from magnetar, which is rotating very slowly, like second rotation. So within this very slow rotation, this kind of emission can be always seen if the direction of the beam is aligned to observer direction. So maybe pulsar radio emission is slightly different.
Thank you.
Any other questions? Suji.
No? Thanks for the nice talk, and this would be quite a nice question, but I'm wondering how can your model can explain the spectral variation in the discussion
Yeah,
number one?
that's a good question. It's your expertise, right? So your paper is here. This is, sorry, I didn't have time. But basically, frequency of this kind of emission depends on the curvature of the magnetic field. Curvature is here, on the bottom here. So basically, if the curvature can be small when there is a multiple, this means it creates high frequency emission, which is often seen in magnetic radio pulsation and also pulsed radio burst too. So this spectral variation can be also expected in multipolar field rather than pure dipole field case. So that's my answer. Is that okay?
Thank you.
Thank you.
Any quick last question right here?
Thanks for a very nice talk. I'm curious about.
Please hold on. Wait for the microphone so everybody can hear you.
Could you go back to the figure you show the flux density versus the time? You classify the.
Sorry, which one?
This one.
This one, okay.
You classify multiple components on the flux density. I'm curious about why the width of different components are different. Width of the peak on the flux density.
Why this is going down?
Yeah, I mean the width of the different components. Because you
Width.
show the different peak.
Yeah. Yeah, I understand.
I'm curious about why they are different because all of the components come from the same megaton, right?
Yeah, this is kind of little more kind of far-fetched idea, so I didn't explain. But this depends on the time scale of acceleration. So basically, the particle, actually, the radiation feature highly depends on many aspects. Lorentz factor of the particle, which is emitting radio emission, and also the curvature radius of the magnetic field. Here and here, curvature is very different, and we don't know whether particle acceleration is the same as here and here. So when discussing spectrum, we have, and also time duration depends on the particle acceleration velocity. So there are a lot of uncertainties. So it's maybe naively, this duration depends on the scale of the curvature. But maybe this sometimes work like millisecond duration, maybe around 10 times larger neutron star radius. This is a time scale for millisecond. So maybe we can, roughly speaking, explain the duration, but the detailed modeling is a little bit, you need more assumption.
Sure. Thank you very much.
Thanks. Good question.
All right, let's thank the speaker again. And our conclusion.